talk.
Thank you.
Okay, our next talk is by Bob Grimm of Southwest Research Institute, and Bob will be speaking about Brecciated crust insulates the lunar mantle, constraints from gravity and electrical conductivity. And Bob, are you ready?
There, now I'm not.
Okay.
I need my computer glasses.
Okay. I understand that.
Waiting for the talk to come up. Okay, well, thanks for listening in, everybody. Today I'm going to talk about some increased temperatures in the inside of the moon, although it's not going to reach the realm of habitability as may be suggested in this still from the Georges Méliès From the Earth to the Moon film. So the starting point for everything I'm going to talk about is a paper I published this year on looking at the geophysical signature of the Procol creep terrain. I'll go over some of those results, new thermal and compositional models, and how those were constrained by gravity, topography, and the electrical conductivity of the moon. The thing that I was really interested in for a couple of years with this project was the possibility that just small changes in the lunar mantle composition could explain the electrical conductivity, and water was a pretty good answer for that, small quantities of water matching what people have been talking about for some time now. But then Grail came along, and the main result that I'll be tying in here is the high porosity of the crust. This implies a low thermal conductivity, which in turn will cause a thermal blanketing and will raise the overall temperature of the mantle. This has no effect on the geophysical anomalies, the lateral contrasts, but rather I'm talking about the bulk mantle temperature going up. But it only goes up by less than 200 degrees, and this is what's different from my abstract for this meeting, which is I'm now going to conclude by saying that the lunar crust cannot be massively porous throughout its entire thickness, as was implied by the Grail team. So the starting point for this discussion is the Procol creep terrain. You're probably familiar with that as this region of anomalous volcanism and geochemical properties, mostly of the Western Maria. Mark Wazorek, as part of his PhD thesis, did a thermal model in which he made a enhanced layer of radionuclides, the so-called creep layer, plastered beneath the crust. He showed that that would extensively melt the upper mantle, which would have some partial melt remaining today. But the most important thing about his work was how he explained the differences in the Apollo heat flow, the Apollo 17 being nominally close to the background signature, and then Apollo 15 being closer to the center of PKT, showing this enhanced signature. So a year or so ago, I worked on reproducing some of his work. My model is a little bit simpler, but it still gets the essential features. When you put the full complement of radionuclides that Wazorek and Phillips used, and you put it beneath the base of the crust, I call that sub H naught, and that's the red line. So you can see it causes this very steep increase in temperature, hot mantle temperatures, and that has the benefit of basically matching barely, as did Mark, the top of the Apollo 15 acceptable limits for the heat flow. That causes very large temperature anomalies in the bulk inside of the moon, melting in parts. And as I'll show you in a minute, that's not desirable for the geophysics. So I sought alternative solutions, trying to put less heating at the base. That didn't work so well. The thing that seemed to work best is to fractionate all of those excess radionuclides, or in this case, I was able to use half of the complement that Mark used, fractionate those into the crust, and you can see that you match then the bottom of the acceptable limits for Apollo 15, still match Apollo 17, and here you see there's hardly any thermal anomaly in the mantle. So the Apollo heat flow can be matched and internal temperatures reduced if the excess radionuclides are fractionated into the crust instead of being at the base of the crust. Now, I also looked at topography and gravity. These are older data, but they're adequate for the analysis at large scales. The first thing you notice is that Procol is a big hole in the ground, negative topography. And then the gravity, this is the lunar prospector gravity. When you filter it to long wavelengths, you can more clearly see that there's basically a regional low of 50 to 100 milligauss. So it's negative gravity. So when you go to try to model the gravity in topography, you see a couple of things. If you take the full complement of radionuclides and a zero lithosphere thickness, in other words, you just let the thermal buoyancy of the interior push the surface up, it will push the surface up by 7 kilometers, which is not observed. This is a mid-ocean ridge scale thermal anomaly and would produce a mid-ocean ridge scale topography anomaly if that were the case. Alternatively, you can impose a thick lithosphere. You can make the surface rigid. In the limit, you would get no topography, but then all the gravity effect is sort of pent up down there below. There's nothing to cancel by making topography. And so if you take that full amount of radionuclides again, and then you say that the lithosphere is infinite thickness, you'll get an 800 milligal gravity anomaly. So you can either have topography or gravity if you choose to put the heat source deep, neither one of which matches the observation. So this is the well-known Whacka Mole problem in geophysics. You cannot simultaneously match the gravity and topography. There's been some suggestion that you could put a layer of basalt over the underlying heat flow anomaly, density anomaly, and mask it. But because the asthenosphere, the hot material, is centered deeper, it's going to have a longer wavelength signature, and so you would still see this parts of this big gravity anomaly around the outside of Procolarum, again, which is not observed. So where I'm going to leave this part of the talk is that I conclude that the PKT heat flow anomaly is not deeply rooted, and it may not be directly related to Mare volcanism. So now we turn to the electrical conductivity. This was measured back during Apollo. It was actually measured only, this particular signature was measured between the Apollo 12 magnetometer and the Explorer 35 satellite, which is co-orbiting the moon at the same time. A year or so ago with Greg Delory, we did some theoretical models. This is an anomalous region of PKT, and we're looking at what its effects would be. But then I went ahead and actually looked at the data. So on the left are a series of graphs that show electrical conductivity with depth modeled as a function of which thermal profile I have, as well as compositional effects were required. On the right is the data. Now this is in frequency versus apparent conductivity. Apparent conductivity is a proxy for the transfer function. So the bottom line is we're trying to get these lines to match this data. So here's the Wazorek and Phillips nominal model. It's very hot. It's too electrically conductive. Here's the background, the remainder of the moon. It's too cold. So to move from Whacka Mole to Goldilocks, we need to find something that's just right. And there's a couple of possibilities for that. Two I show here. We can put extra heat in the mantle. In fact, 3 times increase the background radionuclides 3-fold, and that will give us a pretty decent fit. Or we can put a 5-kilometer megaregolith with a 1/10 of the thermal conductivity of the rest of the moon, and that gets a pretty good match too. Now, as I mentioned earlier, there were also a couple of possibilities to change the magnesium number of the mantle or add some water. So the things I'll be talking about here with the regolith are really upper limits. You could always have some fraction of these effects happening as well. So how does GRAIL play in? Well, GRAIL's exceptionally low altitude gravity measurements allowed the density of topography to be measured. And that means that they could basically infer what the porosity was to a depth comparable to the topography, and that's several kilometers. And the grain density is used to get the porosity. So the implications of that, if you look at this, I don't see my Rasmussen and Warren citation here. Sorry, Warren and Rasmussen, 1987. But you can see that they compiled this data, and here's this box. So if we take 12% porosity, we get something like 0.4 thermal conductivity, watts per meter K, and that's equivalent to a 10-kilometer megaregolith in what I had done before. So 10 kilometers of megaregolith is consistent with the electrical conductivity using a thermal conductivity derived from GRAIL. I'm going to go quickly over this slide. This is just showing the thermal models between 3 billion years ago, cooling to 0. temperatures in the upper mantle of about 1400 K. If you add this megaregolith in, you raise them by 100, maybe 150 degrees. Bottom line, I still can't get the upper mantle to massively melt the way Mark Wazorek did, but I can't have the electrical conductivity much thicker and be consistent with the electrical conductivity. So this is Whacka Mole Part 2. There's no unique solution. So we can actually use the conclusion slide as a point of discussion. The main points that came out of my previous paper were that the creep must be distributed throughout the PKT crust. This underlying creep layer is thin or discontinuous. The PKT radionuclides are not necessarily directly related to Mare volcanism. And thirdly, the upper mantle heat sources for Mare volcanism would be spatially discontinuous or transient. So when I dug up and copped this cartoon from PSRD, which I don't know if you can read it here, has a pretty long lineage going back to Brad Jolliffe, I think that the way the petrologist drew this is almost quantitatively how I would think of it as a geophysicist. Of course, the crustal thickness has been revised down from 60 kilometers to maybe 40, but the main features being that this creep layer, if present, is thin and discontinuous. The entire PKT crust would be creepy. And then the way the petrologists like to draw these little magma source regions down here, I think is geophysically accurate, because we can't have one massive source region for the Western Morea, or else they would have made this giant gravity or topography anomaly. Keep in mind also that something like a third or more of the Morea are not in PKT, and so they have to have some heat source as well. So the main takeaways for this talk, the new things, are that an insulating low porosity crust will raise the internal temperatures by less than 150 K. This is a limit imposed by the Apollo era electrical conductivity of the interior of the moon. And when we place that limit on there, it means the megaregolith thickness can only be 10 or 15 kilometers at this nominal thermal conductivity. So the actual Grail result was several kilometers of megaregolith thickness minimum. I think that's consistent with this result. The modeling that was done in that paper suggests that the porosity could go as deep as 40 plus kilometers into the upper mantle. I don't think that's the case based on these results. We're talking about something like a third to a half of the lunar crust being massively porous. So that's it. Thank you.
Wonderful. Thank you very much. Very nice. Okay, so please type in your questions for Bob if you have any. So Bob, at the start of all of this, when we gave the Shoemaker Award to Bill Hartman, we heard about the megaregolith and its depth, and then how it was consistent with some recent data. And so I'm just wondering, are there some new measurements that you can think of that you'd like to see that would better constrain the thickness of the megaregolith? Because it doesn't seem to actually be well known yet.
Indeed. I think there's new measurements and old measurements. A new measurement, of course, all the geophysicists would like to see a new lunar geophysical network. The capabilities of seismometers now, there are techniques for resolving waves that are passing through the crust a lot better than could be done during the Apollo era. One thing I'm interested in doing is looking back at a pretty forgotten measurement from Apollo 17 called the surface electrical properties. That was sort of a prototype radar, and it may have penetrated many kilometers into the moon. And if we can tease out those results, we might be able to better constrain this porous layer.
Okay, that's great. All right, well, I'm not seeing any questions yet in chat, but that doesn't mean they aren't there. They're probably coming. Please move that over into the general chat room.